So good afternoon, everyone. So in this session, we'll be discussing the last part of the magnetism chapter. The two parts of the magnetism are already discussed in the two sessions, right? So in this session, we'll be discussing the third part, right? The third part of the magnetism will be discussed where we'll be discussing PYQs of the uh, NEET exam that are asked in the previous year exams, right? Now, let's begin with the question number one. The question number one is with respect to the concept that whenever we have one current carrying object in presence of some external field of another object, then the current carrying object will experience some magnetic force, right? In the same manner, when we have two parallel current carrying wires, right? The one current carrying wire will experience magnetic force because of the magnetic field of another wire. In the same way, the second current carrying wire will also face the magnetic force because of the current or because of the magnetic field because of the uh, first wire, right? Now let's suppose these are the two wires here, right? In first wire, the current I1 is flowing, and in the second wire, the current I2 is flowing, right? Then let's suppose the distance between the two wires is T, right? The separation between the two wires is given as T. Then there will be a magnetic force on each of these wires because of the presence of the magnetic field because of the second wire, right? Due to the second wire. Now, the magnetic force here in this case, that will be the magnetic force per unit length, that will be equal to mu naught I1 I2 upon 2 pi d, right? Upon 2 pi d. So this will be the magnetic force per unit length experienced by one of the wires because of the presence of magnetic field due to another wire, right? So this is the magnetic force per unit length, right? So in the same fashion, we have been given two long and parallel wires at a distance of 0.1 meter, and a current of 5 ampere is flowing in each of these wires, right? So the separation between the two wires has been given as 0.1 meter, and the current flowing through each of these wires is 5 amperes, right? The force per unit length due to these wires will be, right? So the force per unit length we can calculate directly by using this equation. That's F by L. It will be mu naught I1 I2 upon 2 pi times the distance between or the separation between the two wires, right? That is T, right? So the value of I1 and I2 is given as 5 each. So it will be 5 into 5, that will be 25 upon 2 pi multiplied by the distance, that is given as 0.1. So the magnetic force per unit length will be mu naught times 25 upon pi, right? So we can substitute the value of mu naught here in this equation, that is 4 pi into 10 to the power minus 7 multiplied by 25 upon pi, right? Upon pi. So from here, pi and pi will get cancelled. So 25 into 4 will be 100, or we can write it as 10 to the power minus 5 newtons per meter, right? So this will be the force experienced by one of the wires because of the presence of the magnetic field due to other wire, right? And both these forces will be equal and opposite in direction, right? And when the two currents are parallel to each other, right? When the two currents are parallel to each other, then the force is attractive. And if the two currents are anti-parallel to each other, then the force will be repulsive, right? So the force here will be attractive force. It means that this wire will be attracted towards this wire, and this wire will be attracted towards this wire. So this will be the direction of the forces on the two wires, right? Now let's move on to the another question with respect to the same concept is involved in this question as well, right? So in this question number 2, we have been given three long straight wires carrying currents as arranged according to the figure, right? Magnetic force on 20 centimeter part of the wire B is, right? You can see here there are three wires A, B, and C, right? In the wire A, the current 3 ampere is flowing. In wire B, the current 6 ampere is flowing, and in the wire C, the current of 8 ampere is flowing, right? The separation between two consecutive wires is given as 4 meter, right? So A and B is 4, and B and C is also 4. So it means that there will be some magnetic force experienced by wire B because of the presence of the magnetic field of other two wires, right? Now, since let's talk about the number of forces acting on this wire B. One force will be the attractive force because of this wire C, because we know that both the wires are parallel wires, and because both the currents are parallel currents, and the parallel currents attract each other, right? And the anti-parallel currents will repel each other, right? So there will be attractive force between the two wires B and C, right? It means that B will be attracted towards C. It means the direction on B, direction of force on B because of the C will be towards the wire C, right? And similarly, the direction of the force because of wire A on B will be towards the wire A. It will be attracted towards wire A. Now we can call this force as FA and this force as FB, right? FB. Now FB, that will be force per unit length because of wire C, right? Because of, let me call this FC, not FB, it will be FC, right? This is FC. So force per unit length because of wire C will be nothing. It will be equal to mu naught I1 I2 upon 2 pi d, right? Upon 2 pi d. The separation between the wire B and C is given as, it's given as 4 meters, right? We can substitute the values of current. I1 is given as 6 and I2 is 8 upon 2 pi multiplied with the separation between the two wires, that is given as 4, right? So from here, this 8 and 4 multiplied by 2 will get cancelled, will be cancelled. So it will be 6 mu naught upon pi. So this is the attractive force because of wire C on the wire P, right? Now similarly, we can calculate the attractive force on wire P because of wire A force per unit length, that will be mu naught I1 into I2 upon 2 pi times the separation between the two wires, right? So the value of I1 here is that's 3 and I2 is 6 upon 2 pi d. So d here is once again 4. So it will be 12 upon 8 multiplied by mu naught upon pi, right? So we can write it as 3 upon 2 mu naught upon pi, right? So this will be the attractive force per unit length because of the wire A. Now the net attractive force per unit length will be actually it will be Fc minus Fa, right? It has to be Fc minus Fa. So we can write Fc upon L minus Fa upon L, right? That will be equal to, it will be 6 mu naught upon pi, right? Minus 3 mu naught upon 2 pi, right? So it has to be equal to, so 12 minus 3 will be 9, right? It has to be 9 mu naught upon 2 pi, right? 9 mu naught upon 2 pi. So 9 mu naught upon 2 pi will be the net attractive force, right? It will be the net attractive force on the wire P because of the two wires A and C, right? And now we have to find the force on 20 centimeter part, right? So force on B, net force on B will be uh, and 9 mu naught upon 2 pi multiplied by the length, right? The length is 20 centimeters. So on 20 centimeter part, it will be 0.2, right? So it has to be equal to 0.9, right? 0.9 mu naught upon pi, right? This much will be the force, right? Or we can write it as 0.9 into 4 pi into 10 to the power minus 7, right? Upon pi. So pi and pi will get cancelled. 4 into 9 will be 36. So the value of FB will be nothing. It will be 3.6 into 10 to the power minus 7 newtons, right? So this much of force will be there between the two wires, right? So this will be the net force per unit, net force on 20 centimeter part of wire P, right? On 20 centimeter part of wire P, right? Okay. So this is how we can calculate the net force, right? Now let's move on to the question number 3, right? Moving on to the question number 3, the question 3 says that what is the net force on the square coil, right? We have been given a square coil, right? The dimensions of this square, it's not a square coil, actually it's a rectangle. Here you can see the dimensions of this coil is for one side is 10 centimeter and another side is 15 centimeter, right? So we can call it as a rectangle, right? It's a rectangular coil, not a square coil, right? So we have to find the net force on this rectangular coil, right? We have to find the net force on this rectangular coil, right? Now let's denote this rectangular coil by A, B, C, and D, right? Now there are four sides of this rectangular coil, right? On each of the side, there will be a magnetic force because of the wire through which the 2 amperes of the current is flowing, as shown in the figure, right? The separation has been given as 2 centimeters, right? And the current in the wire, current in the rectangular coil itself is given as 1 ampere, right? So 1 ampere current is flowing through the 1 ampere current is flowing through the rectangular coil, right? Now, what we'll do here is that we will just try to find the force on each of these sides on the rectangle, then calculate the net force will give us the total force acting on this rectangular coil. Now, let's begin with the side A, right? Let's begin with the side A. Now, talking about the force, there will be some magnetic force acting on the side A of this rectangular loop, right? Now, talking about the direction of the magnetic force acting on this loop AB, right? Acting on this loop AB, right? So the magnetic force on this loop AB will be the direction of the magnetic force on this side AB will be it will be given by dl cross b, right? It will be given by dl cross b. Now the length of this dl, the direction of this dl vector is along the direction of the current in AB, right? And the magnetic field in this region is into the plane of this paper. It means that the direction of the magnetic force will be along this direction. So this will be the direction of the magnetic force, right? And similarly on this side, the direction of dl vector is along this direction, and the magnetic field is once again into the plane of this paper. So the magnetic force will be along downward direction. You can see here the magnitude of the magnetic force acting on AB will be equal to the magnetic force acting on CD. It means that but the two forces will be opposite in direction. It means that the magnetic force on AB will cancel out the magnetic force on CD. So we will not consider these two forces, right? Because these two forces will get cancelled out because they're in opposite direction, right? And they will be in a same in magnitude, right? Now talking about the magnetic force on this wire AD and BC, we are left with the two wires, right? AD and BC. So magnetic force on AD will be nothing. The length of this AD is given as 15 centimeter, right? So the magnetic force on AD portion will be F, right? It will be towards it, towards the wire, because we know that the parallel currents actually attract each other and the parallel currents repel each other. So FAD will be equal to mu naught I1 into I2. That will be 2 into 1, right, multiplied by the length of this AD, that is 15 centimeter. We can write it as 15 into 10 to the power minus 2 upon 2 pi d. D is the separation between the two wires, that's given as 2 centimeter. We can write it as 2 into 10 to the power minus 2. This and this will get cancelled, right? This and this will also get cancelled. Will be left with 15 mu naught upon 2 pi. So this will be the magnetic force on AD part, right? Now let's calculate the magnetic force on BC part. Magnetic force on BC part will be nothing. It will be mu naught I1, I2. Since it's anti-parallel current, so the magnetic force will be repulsive in nature. It will be along this direction, right, on BC part, right? So mu naught I1, I2, it will be 2 into 1, right? The length of this portion is 15 centimeter. And once again, that will be 15 into 10 to the power minus 2 upon 2 pi d. The distance between separation between this wire and this BC here is, it has to be 12 centimeters, right? It will be 12 into 10 to the power minus 2, right? So this and this will get cancelled, right? So this 2 and 2 will get cancelled. We'll be left with, so 15 upon 12, we can write it as 5 upon 4, right? 5 upon 4. So it will be 5 mu naught upon 4 pi, right? So this is FBC, right? FBC. So the net force F net will be nothing. It will be the subtraction of the two forces, right? It will be subtraction of the two forces. That will be 15 mu naught upon 2 pi minus 5 mu naught upon 5 mu naught upon 4 pi, right? So the net force will be equal to, it has to be equal to 30, it will be 25 mu naught upon 4 pi, right? So this will be the net force, right? So this will be the net force acting on this coil, right? 25 mu naught upon 4 pi. We can substitute the value of mu naught here in this equation. That will be 25 multiplied by 4 pi into 10 to the power minus 7 upon 4 pi, right? So this and this will get cancelled. So 25 into 10 to the power minus 7 newtons will be the net force acting on this coil, right? 25 into 10 to the power minus 7 newtons will be the net force acting on this rectangular coil, right? And let's move on to the next question, question number 4, right? The question number 4 says that a straight steel wire of length has a magnetic moment M. A straight steel wire of length L, right? It's actually of length L, right? Has a magnetic moment M. It is bent into various shapes as shown in the figure. Find out new magnetic moment of each case shape, right? Now let's suppose we have a wire, right? The wire has the two poles, right? Two magnetic poles. One is the minus M, another will be plus M, right? So these are the two magnetic poles of the wire, right? Of length L. Now the magnetic dipole moment of this wire will be nothing. It will be the pole strength multiplied by the length, right? So this will be the magnitude of the magnetic dipole moment, right? Now what we have done is that we have bent this wire of length L into two different shapes, right? The first shape has been as shown in the figure, right? We have this side L by 2, this side L by 2, right? This is one pole of this magnetic magnet, right? This is another pole of this magnet, and we know that the magnetic moment, dipole moment will be nothing. It will be the pole strength multiplied by the distance between the two poles, right? Now let's suppose that the distance between the two poles will be here. It's L by 2. It will be L by 2. So it has to be L upon root 2, right? It has to be L upon root. So the magnetic dipole moment of this portion will be, or this shape will be equal to pole strength M multiplied with the distance, that is L upon root 2. So we can write it as M dash will be nothing. It will be M upon root 2, right? It will be M upon root 2, right? Similarly, for this shape, it has been bent into a triangle, right? Like this. If this is 60, this has to be 60, and this has to be 60 as well, right? So this side will also be equal to L by 2. It means that it will behave like an equilateral triangle. So there are two poles of this magnetic dipole, right? So this is negative pole, this is positive poles. The separation is L by 2. So the magnetic moment for this shape will be ML upon 2, or we can write it as M by 2, right? So it will become half for this shape, and it will be M by root 2 for this shape. So this is how we can find the magnetic dipole strength, right? Magnetic dipole moment, right? Now let's move on to the question number. Next question is the question asked in one of your previous year exams, right? A magnetic moment is given as 50 I cap a ampere meter per square ampere meter square placed along x-axis. So it means the direction of this magnetic moment is given along the direction of the positive x-axis, right? It's 50 I cap. Here magnetic field is given as 0.5 I cap plus 3.0 J cap Tesla, right? The torque acting on magnet is the torque acting on the magnet is nothing. It's given as magnetic moment cross producted with the magnetic field, that's M cross B, right? So the value of M is given as 50 I cap, right? 50 I cap. We have to cross product it with magnetic field, that's 0.5 I cap plus 3.0 J cap, right? So 50 I cap. I cap cross I cap is 0, right? And I cap cross J cap has to be a K cap, right? So it will be 50 into 3, it will be 70, 150, right? It will be 150 K cap, right? So this is the net magnitude of the torque acting on this magnet, right? 150 K cap will be the net torque on this magnet. Now let's discuss the question number 6. A helium nucleus is moving in a circular path of radius 0.8 meter. If it takes 2 seconds to complete one revolution, effective current, find the effective current, induced magnetic field at the center, magnetic moment, right? Now let's suppose that we have an atom, right? At we have an atom, right? And according to Bose model, the electron actually revolves around the nucleus of an atom in circular orbits, right? So we can say that this circular orbit will behave like a current loop. It will behave like a current loop, and there will be some magnetic field at the center of this atom, right? Because of this electronic charge moving in a circular loop, which behaves as a current loop, right? So the magnetic field at the center will be magnetic field due to a current loop, that will be mu naught I upon 2r, right? Let's suppose the radius of this loop is r. So the current magnetic field at the center will be mu naught I upon 2r. Now this current I is nothing. It will be the charge q upon the time t, right? So the charge here is e, and the time period will be t, right? Now let's suppose this charge electron is going with the speed v, right, in this circular orbit. So the time taken to complete the one revolution will be the circumference upon the circumference upon the velocity or speed of this electron in circular orbit, right? So this will be the time period. Now we can calculate the value of current here. It will be E 2 pi r into V, right? So EV upon 2 pi r will be the current, right? EV upon 2 pi r will be the effective current, right? Now talking about the magnetic field, induced magnetic field or induced magnetic field at the center, BC, that will be equal to mu naught I, the value of I is given as EV, right, upon 2 pi r. So it will be 4 pi r square, right? It will be 4 pi r square. So this is the net magnetic field at the center of this atom, right? And this will actually behave as a magnetic dipole. We know that current loop behaves as a magnetic dipole, so it will have some magnetic movement. The magnetic movement M will be nothing. It will be I multiplied by A, right? Current multiplied by the area. That will be the magnitude of a magnetic movement. So the current here is actually EV upon 2 pi r, right? This is the current multiplied by area, that will be pi r square, right? So from here pi and pi will get cancelled, r and r will get cancelled, will be left with the magnetic moment as EVR upon 2. So this is the net magnetic moment, right, at the center. Now for this helium nucleus, you know that for this helium nucleus, the radius of the circular path is given as 0.8 meter, right? If it takes 2 seconds, so the time period is also given, right? you can calculate all the other quantities for this question, right? You can calculate the effective current, you can calculate the induced magnetic field at the center, you can calculate the magnetic moment as well. So I just gave a brief about the concept that how we can calculate the magnetic field because of the electronic charge moving in circular orbit and magnetic dipole moment or magnetic moment because of that circular charge moving in a circular path in a given atom, right? So that's what how we can do it, right? Now there is another quantity, another important concept that we call as gyromagnetic ratio, right? Gyromagnetic ratio, right? We'll be discussing a bit about the gyromagnetic ratio, right? It's a very useful quantity to calculate the magnetic moment of different objects, right? We'll be discussing a brief about the gyromagnetic ratio, right? Now we know that when electron moves in a circular orbit of radius r with velocity v, so its angular momentum will be actually a conserved, it will be a quantized quantity, right? It will be a quantized quantity and it will be always equal to in a given orbit mvr, where v is the velocity of that orbit and r is the radius of that orbit, right? So this is the angular momentum, right? Angular momentum. Now the magnetic moment, we know that it's nothing, magnetic moment we calculated, it's EVR upon 2, right? EVR upon 2, right? EVR upon 2. I will calculate the ratio of this magnetic moment and the angular momentum L, right? So it will be EVR upon 2, EVR upon 2 into MVR, right? Into MVR. So from here, VR and VR will get cancelled. We'll be left with E upon 2M, right? E upon 2M. This is what we call as nothing. This is, we call it as gyromagnetic ratio, right? Gyromagnetic ratio. Gyromagnetic ratio, right? It's a very useful quantity to calculate the magnetic moment for different objects, right? For different objects. So in general, if E is the charge, if any other charge Q is moving in a circular orbit, then we can replace the charge of the electron with the charge of that object, right? So it will be m by L. In general, it will be Q upon 2m, right? Q upon 2m. So m by L is always equal to Q upon 2m, right? So this equation we can use to calculate the magnetic moments of different objects. That's the gyromagnetic ratio. M by L is equal to Q upon 2m, right? Now let's suppose I have a let's suppose I have a coil, right? Or ring, right? Let's suppose we have a ring. This is the ring, and the charge on this ring is given as Q, right? Charge on this ring is given as Q. Q is the net charge on this ring. If Q is the net charge on this ring, right? Q is the net charge on this ring, and the radius of this ring, let's suppose, is R. Now, this ring is actually rotating about its own axis, right? With an angular velocity of omega. Then angular velocity of omega, right? So, so there will be some current because of this ring, because the charge is rotating, charge is moving, right? There will be some current. So there has to be some magnetic moment as well, right? Because of this ring. Now, if we want to calculate the magnetic moment because of this ring, the magnetic moment is nothing. It's the charge upon 2m multiplied with the angular momentum L. So charge we know Q, mass of this ring is given as m, right? But we have to calculate the angular momentum. So angular momentum, we know that will be nothing. It will be about this axis. That will be I omega, right? And I is the moment of inertia about this axis. For the ring, moment of inertia about this axis will be mr square, right? Mr square omega, right? So the magnetic moment, we can just let's write the mass of the object with small m, right? So magnetic moment with a capital M. So it will be Q upon 2m multiplied by the angular momentum. That will be mr square omega, right? Mr square omega. So m and m will get cancelled. So half of Q omega r square is the magnetic moment because of this ring, right? Similarly, if we have suppose disk, we can have disk, right? We can have disk. For the disk, the magnetic if the disk is rotating, then the moment of inertia for the disk about its axis passing through the center, right? It will be mass square upon 2. Similarly, for sphere, we have 2 by 5 mr square. So we can calculate the magnetic moment due to different objects. We can calculate magnetic moment due to cylinder, due to sphere, due to disk, due to ring. So this gyromagnetic ratio is a very useful quantity, right? To calculate the magnetic moment due to different objects which are actually rotating about their axis, right? So that's about the gyromagnetic ratio, right? Let's move on to the another question, right? This question is a very it's a very usual question, right? It is very frequently, such questions are very frequently asked in the competitive exams, and this question was also asked in the uh, January session of one of your competitive exams, right? So an electron moves through a uniform magnetic field, right? That's given as magnetic field is given as B naught I cap plus 2 B naught J cap Tesla. At a particular instant of time, the velocity of electron was 3 I cap plus 5 J cap meter per second. If the magnetic force acting on electron is given that's 5 E K cap newtons, where is the charge of electron, the value of B naught is. In terms of Tesla, we have to calculate the value of B naught. We know that the magnetic force acting on a charge which moves at an angle of theta with respect to the magnetic field, that has to be equal to q v cross b, right? So this is the magnetic force acting on a charge moving in some magnetic field, right? So here the charge moving is charge of electron. We'll replace it with v. We have to calculate the v cross b, right? So let's determine this value v cross b, right? It will be E times v is given as 3 I cap, right, plus 5 j cap, and cross protected with b naught I cap plus 2 b naught J cap, right? So we will calculate the cross product here. Now I cross cap, I cross is actually 0, and I cross cap, I cross J cap will actually give us K cap. So 3 into 2 will be 6. 6 B naught, right? K cap, right? Now J cross I has to be minus K, right? J cross I will be minus K. It will be 5 B naught minus K cap, right? And j cross j will be 0 actually, right? So net magnetic force we is that's equal to b naught e k cap newtons. So this is the net magnetic force we calculate, but this magnetic force has been given equal to 5e upon 5e k cap, right? 5e k cap newtons, right? So from here we can just say that uh, the value of b naught is actually 5, right? The value of b naught is comes out to be 5, right? So the value of b naught comes out to be 5 from this equation, right? So it is 6 b naught k cap minus 5 b naught minus 5 b naught k cap, right? That's b naught k cap, right? And it is given equal to 5 e k cap. It means the value of b naught is 5, right? So 5 will be the correct answer for this question, right? 5 is the value of the b naught for this question, right? And let's move on to the another question. The magnetic field at the center of a wire, a loop formed by two semicircular wires of radii r1 and radii r2. Radii r1 is given as 2 pi meters and the r2 is given as 4 pi meter, carrying current I equal to 4 amperes as shown in the figure, right? The figure I will be drawing, right, is alpha into 10 to the power minus 7 Tesla. The value of alpha is, right, the figure is like this. So the situation is like this. So this is the given situation in this question, right? Now for the first coil, the radius is r1, and for the second coil, the radius is r2, right? So we have to find the magnetic field at the center. So the net magnet, let's suppose there is current I flowing, and this current I is given as 4 amperes, right? So the same current I will be flowing through this, right? Now if we calculate the direction of the magnetic field because of this circular portion, it will be into the plane of this paper. We'll be using the right hand thumb rule, right? It will be into the plane of this paper, and because of this larger semicircular wire, it will also be into the plane of this paper, right? It means that two magnetic field will actually add up at the center, right? It will actually add up at the center, right? That's the center O, which is common for both the segments, right? So the net magnetic field will be, and we know that the magnetic field due to an arc is nothing, it's mu naught I alpha upon 4 pi r, right? 4 pi r. Now it's a semicircular arc. Now you can say the angle alpha that will be subtended at the center of this arc will be 180 degree, that will be pi. So we can replace it by pi. So we'll get the magnetic field because of semicircular wire, that's mu naught I upon r, right? Mu naught I upon r. So because of both these semicircular portions, the magnetic field is along the same direction. So the net magnetic field will be mu naught I upon 4 times r1 plus mu naught I upon 4 times r2, right? So from here we can take mu naught I upon 4 as common, 1 upon r1 plus 1 upon r2. R1 is 2 pi and r2 is given as 4 pi, right? So taking some LCM from here, right, it will be mu naught I upon 4, right? It will be 3 upon 4 pi, right? 3 upon 4 pi. So from here, we can replace value of I, and the value of I is given as 4, right? And mu naught is 4 pi into 10 to the power minus 7 multiplied by 4 into 3 upon 4 into 4 pi, right? So 4 pi and 4 pi will get cancelled, right? 4 and 4 will get cancelled. We'll be left with the net magnetic field at the center. That will be 3 into 10 to the power minus 7 Tesla, right? So this is the net magnetic field. So from here, comparing the two results, the value of alpha comes out to be 3. So 3 will be the value of alpha, right? Now let's move on to the next question, right? The next question is that a singly ionized magnesium atom ion is accelerated to kinetic energy 5 kilo electron volt and is projected perpendicularly into a magnetic field B of magnitude 0.5 Tesla. The radius of path formed will be, right? We have to find the radius of the path, and we know the radius of the path is nothing that's given as mv upon qb, right? mv upon qb, where mv is the momentum, right? mv is the momentum and q is the charge and b is the magnetic field, right? So we can replace this mv with the momentum, that will be p upon qb, right? And we know the relation between the kinetic energy and momentum of a particle is that p square upon 2m is equal to kinetic energy of the particle, right? So we can replace, write this momentum in terms of kinetic energy, that will be 2mk under root, right? So this is the momentum in terms of the kinetic energy. So we can replace this momentum in this equation, right? That will be under root of 2mk upon qb, right? So now we got the equation of radius of the circular path, right, in terms of the kinetic energy of the particle, right? Now, the kinetic energy of the particle is given as 5 kilo electron volts, right? Kinetic energy is given as 5 kilo electron volts. That will be 5 into 10 to the power 3. Electron volt, that is 1.6 into 10 to the power minus 19, right? Now, the charge has been given as, since it's a singly ionized magnesium atom, so the charge will be the charge of electron, that's 1.6 into 10 to the power minus 19 coulombs, right? Now, the magnetic field is also given as, that's equal to V, that's equal to 0.5 Tesla, right? Now, talking about the mass, right? So the mass of this, in terms of the mass of a single magnesium atom is actually 24 atomic mass units, right? So each atomic mass unit is approximately 1.67 into 10 to the power minus 27 kg. So for 24 atomic mass units, it will be 1.67 into 10 to the power minus 27 kgs, right? So this much will be the mass of this atom, right? You can substitute all the values of kinetic energy, charge, magnetic field, and mass of this magnesium atom, right, to calculate the radius, right? Now let's move on to the another question. A beam of protons with speed 4 into 10 to the power, a beam of protons with speed 4 into 10 to the power 5 meter per second, right, enters a uniform magnetic field of 0.3 Tesla at an angle of 60 degree to the magnetic field, right? The pitch of the resulting, so the angle between the velocity vector and the magnetic field vector is given as 60 degree, right? The pitch of the resulting helical path of protons is close to. We know that whenever an angle between the magnetic field and the velocity vector is other than 90 degree, then the path followed by the charge in a magnetic field is helix, right? It's helical path, right? It will be a helical path, right? Now, the particle will try to move in a circular path because of the perpendicular component of its velocity, and it will drift towards the right, or it will drift towards the right. There will be drift towards the right because of the horizontal component of the velocity, and that drift in one complete time period of the circular path. That's what we call as the pitch of this helix, right? That's what we call as the pitch of this helix, right? Now, to calculate the pitch of this helix, we have to just use this equation, that will be time period multiplied by the horizontal component. That will be v cos of theta, right? If theta is the angle between the magnetic field and the velocity vector, right? So this will be the pitch. So talking about the time period is nothing. It is 2 pi m upon qb, right? 2 pi m upon qb is the time period of the 2 pi m upon qb is the time period of what we call as circular path, right? We have to calculate the horizontal component of the velocity, that's v cos theta, that will be multiplied by. So this is the time period. Talking about the pitch, it will be 2 pi m upon qb, right? Multiplied by the horizontal component v cos theta, that will be 4 into 10 to the power 5. Cos of 60 degree is 1 upon 2, right? From here 2 and 2 will get cancelled. Now you can substitute the values here. Now the mass of proton is given as 1.67 into 10 to the power minus 27 kgs, right? So we can replace the value of pi. Pi is given, and the charge is will be the electronic charge, right? Q, and mass is also given, right? 4 into 10 to the power 5. We can substitute the value of m equal to 1.67 into 10 to the power minus 27 kgs here, and you can substitute the value of a charge of proton C, charge of proton Q, right? That's given as 1.69 into 10 to the power minus 90. coulombs. So substituting these two values, mass and charge, will get the pitch of this helix, right? So pitch of this helix, it's a very simple quantity to calculate, right? If the velocities and the magnetic field is given for the given conditions, right? So with this question, we have actually almost touched each and every portion of this chapter, magnetism, right? We have almost completed this chapter with respect to a coming NEET exam, right? All the things have been actually completed, right? We'll be shifting to a new chapter in the next lecture, that will be electromagnetic induction and the alternating current, right? So uh, in the next lecture, we'll be starting with the alternating current and electromagnetic induction. So till then, take care and goodbye.